Right, so this video is all about kinetics from the AQA AS specification. Kinetics is one of the easier topics, yet sometimes can trip people up based on funny questions when it talks about changing things like temperatures and pressures and all the rest, which hopefully I'll go through in this and people will be absolutely okay, at least answering afterwards. So, kinetics. What is kinetics? Well, kinetics is this idea really of it's the easiest way I think to explain it is it's comparable, if not almost identical, to the kind of rates of reaction topic that you would have done at GCSE, which I'm pretty sure is in all specifications. You know, EdXL, OCR, AQA. You know, I would guess the Cambridge IGCSE and all the rest. And so, just a starting point really is to say, well, let's think of a reaction. This reaction, my old favourite, A plus B going to C plus D. So this is a delightful chemical reaction of some generic chemical compounds that have reacted. Two reactants, two products. It's fine. How does reaction occur? Well, this reaction occurs because A and B collide. So A and B must come together into a collision. Now, that's the very crucial thing, and this comes under the guise of collision theory. And really, there's a lot to be said about collision theory because it as far as I'm aware, it has quite an important effect on chemical reactions and all the sort. So collision theory, they've collided. We have a collision. Two things can happen. One, nothing. Fairly easy to remember that. You just have to remember that nothing happened. That's the first option. The second one, reaction. So they're the two options. The first one, they literally simply bounce off each other, go their separate ways, probably never to meet again. A and B come together, they react and we produce C and D. That's a great thing. Now, that reaction, it's very important. If that reaction is to occur, then the energy of the particles must be greater than or equal to the activation energy, the energy of activation. And that is this thing here. And if you look at energetics, which is also in this topic, in this unit, I should say, the activation energy is the energy required, it's the minimum energy required for the reaction to take place. So if we do not have that activation energy, we are not going to get a reaction. It's like a fee to get into a gig. It's the price to go to the cinema. It's the it's the cost of your shopping. If you haven't got enough, you're not getting it. That's the end of it. So that's the options: nothing or reaction. To build on the GCSE very slightly and to kind of recap in some ways, you have, and it has come up I think once certainly, I still expect to have that GCSE idea, and the best way to sort of talk about that is to show you a kind of a GCSE type graph. So something like this one. Now this is a graph that is showing us a reaction of which, whatever it is, I don't know what it is, maybe decomposition of hydrogen peroxide, it could be anything. We're producing oxygen, and we're producing it over time. Now we're going from this point here, and we're going up here. So it's a completely qualitative graph. There's no numbering associated with it, it's just completely qualitative. Now there are a few kind of questions that can be asked about this. So the question could be, we could find that this reaction, and I'm just going to pick some numbers out of the air. So we found that to get this curve, 100 centimeters cubed of 1 mole decimeter cubed hydrogen peroxide was used. And that's what gave the curve R. Now let's think, well, what would happen if I were to use a concentration that were different? So say I were to use, I don't know, 0.5 mole per decimeter cubed. So we've got half the concentration, therefore the reaction is going to only reach half the point that it got to previously. But it's also less concentrated, and therefore it's going to occur more slowly. So in this case, we're going to find that we're going to reach half the position we reached previously. So we're going to get to about this point here. No, we're not. We're going to go a bit lower than that actually. We're going to go about 1 1/4. To count these lovely lines they've given me here, and obviously we're not going to get there at the same point. It's going to be slower to get there, and there we go. We have our nice line continuing across. So really the important thing here is that the curve is shallower than the other one. That implies that a slower rate of reaction, and certainly the height, or the maximum height that the curve reaches, this straight line here, is at a correct proportion to the original. So I've gone for half of the original because I'm using half of the concentration. I could get something different, and so this would be line Q, for example. Let's have a look at if I were to do line P, and we could say that P is at 2 moles per decimeter cubed. Now in this case, I'm increasing the concentration. And think back to this, I didn't explain that really in this case. When we increase the concentration, we've got more particles, this will come up later, more particles in a given area, or a given volume, sorry, and therefore more collisions, therefore a higher chance of collisions taking place. Therefore the reaction rate would increase. The opposite is true for here. Less molecules in a given volume, less collisions, and therefore statistically a lesser chance of successful collisions, or a less chance of a successful collision. So I've increased the concentration, my rate of reaction is going to be increasing. I'm going to go to double where I got to before. So I'm going to hit this line up here. Boom, there we go. Hopefully your lines will be straighter than mine, and we've leveled out at that level here. So I've got to the point where I've gone to double, because I've got double the concentration, therefore double the amount of moles, and therefore double the potential of oxygen to be produced. And I've got there quicker, because here we go, steeper line. Steeper, more shallow means it's slower, even more shallow means it's slower again. Final line, I could say, well, and let's see if I've got another colour for this. Yeah, just about. I could say, well, line X was at a higher temperature. And again, this is GCSE. Higher temperature means we've got more energy, faster, more frequent collisions, and therefore more successful collisions. This rate of reaction is going to be quicker, but we've not changed the amount, so I'm still going to get to my same ending point. So factor that across to about here, but I'm going to do it quicker. So there we go, up and oh, in fact, you know what? Just redo that one. There's my point I'm going to reach. I'm going to go up, and there I'm going to go. Bit better than last time, and I'm going to go right across. That there was line X, this was line P. So that's just another way to think about this kind of whole rates of reaction. Now, as an extension really of GCSE, which was relatively straightforward really when it came to rates of reaction, in all honesty, those ideas still stand true. We look at something now called the Maxwell-Boltzmann distribution curve, and that looks something like this. So I've got a delightful set of axes that I've drawn incredibly professionally, and these axes, as far as I'm aware, you would be given these in an exam, and you'd be giving a line on them. And now they have, obviously we need some labels. This one, number of molecules, or particles would work as well. And this one, energy. Just generally energy. Now, the distribution curve looks something like this. I might be able to do this first time, but we'll see. So it starts about here, it goes up, and then it comes down, and off like that. Not touching zero. Okay, that's important because you will potentially have to draw this yourself. Not touching zero. Now this is my normal distribution curve for my whatever, for a set temperature. Temperature, what should we say? Temperature A. So temperature A. Don't know why I've written that there and there, but there we go. So A Kelvin. A couple of things about this. We can say that, well, no particles have zero energy. That's fairly clear. No particles can have zero energy. That's ridiculous. Majority of the particles have this sort of energy, and the area under here equals the number of molecules in total. Actually, the area under here is the number of molecules, the total number of molecules. And what this is here, so here this axis tells me that it gives me the total number of molecules at a given energy. Now this one here, this point right here, which comes down to about here, would be the most probable energy. I'm not saying it's the average energy, it's the most probable energy. It's the energy that most particles have. This one around about sort of here, this point there. Onto this, we can also write down, we can also put on something like the activation energy. And so I can draw a delightful line like this. And I could say, well, this is the activation energy. Right there, that is it. And actually now the idea of this rates of reaction becomes a lot more, it becomes a little bit easier to understand, because we can see, well, all these particles do not have enough energy. These particles do. That's a good thing. Particles have more energy. Particles do not have enough energy. They must at least be at this line, okay? So we have this number of particles that can indeed react. So the area here is the number of particles that can react. That's your basic Maxwell-Boltzmann distribution curve then. It's fairly straightforward. Now, you're going to be given this an exam. What they're probably going to do is they're going to say to you, a student increases the temperature. Draw onto this, sketch a curve to show the distribution curve for this reaction at the increased temperature. So we could say temperature is going to be, now we're looking at it at temperature B. So B Kelvin. So this was our line at A Kelvin, which was lower. So B is, A is smaller than B. Okay, so we draw a line here. So A is going to be, we're saying that A is smaller than B. Sorry, I forgot what I was even saying there. So B is at a higher temperature. Well, when we have a higher temperature, we're going to get more particles that are going to be above the activation energy. So we draw onto this a new line, and that new line needs to accommodate that fact. I'm going to get rid of this number of molecules in the middle because it's going to overlap what I'm doing. There's a couple of things when we're drawing the line. I'll draw the line first, and I'll explain a few points. So it starts at the same point, it goes like this, and then it goes like this. So key thing is, at a higher temperature, this B shifted right. That's a very important thing. It has been shifted to the right. So the peak could be a little bit better than this, I'm not going to lie. The peak should be really, ideally would be a little bit further over there. But there we go. It could be better, it could be worse. Key thing is, it's been shifted to the right. It's lower than before. Okay, and what we find is that generally we have more particles, certainly this area now, we have this whole area where particles have greater than the activation energy. So in increasing my temperature, I have significantly increased the number of particles with the required activation energy. So increase the temperature, more particles have greater than or equal to the activation energy, and the end result of that is that we get more successful or productive collisions. Easy. So that's very similar to really the GCSE, the kind of answer we're looking at, and this is any question where they're talking about the idea of how does the increase in temperature increase the rate of reaction. This is the kind of answer you're going to be throwing out. More particles have greater than or equal to the activation energy. Or you could say significantly more particles have greater than or equal to this activation energy. Therefore, more successful collisions. And we could flip it the other way around. I could say, well, what happens if I decrease the temperature? So let's decrease temperature. Now this time, we'll try and draw this one a little bit better. Oh, a bit dodgy there. Okay, yours doesn't really want to have that little bit there, and they would probably give you a line higher than the black line that I drew. I probably should have thought about that, but there we go. This time, I'll try and get my arrows the right way round. So A is bigger than C, so, oh dear, I should have labelled these really. C Kelvin. B Kelvin. I apologise about this in advance. So, at C Kelvin, which is lower than my initial A, it has been shifted left. Okay, I've shifted it to the left. That's very important because now we find that most of our most probable energy is now lower, as we would have expected, versus the higher temperature there and now medium temperature there. And again, as we expect here, it drops down and we get this delightful line down here. It's beautiful. Work of art. We actually find the area under this part actually now is smaller, therefore there are a fewer number of molecules that have the required activation energy, which gives us now the link into our rate of reaction, which if we were to change this and we were to say that we decrease the temperature, less particles, the wonders of computers, and less successful collisions. So reasonably straightforward there. A couple of things about when you're drawing these curves. First of all, make sure it's shifted to the left and shifted to the right. This should be higher, whereas, very important, and this might seem picky, this should be lower than the original peak. And there are marks in the exams. The examiner's going to look for a couple of things. Going to look for it to be shifted to the left in the case of the lower temperature, and for it being higher, shifted to the right and lower. The other thing he's going to look for is that your new line only crosses the original once. And if you look at this, it's difficult because I've got all three on here, I know. But if you look at this here, my lower temperature line only crosses the original one once there. The rest of the time it does not cross. Terribly at the bottom, I know, but there we go. Higher temperature one only crosses once. It does not cross again, and that's very important. Your line starts crossing like this. It's a roller coaster. You're going to lose the mark instantly, and that's not something you want to be doing. So that's the Maxwell-Boltzmann distribution curve. Now, one other thing actually to add before I forget that is how catalysts affect the rate of reaction. Now, a catalyst decreases the activation energy, and in this case, that actually makes this quite easy. Decrease the activation energy, well, we just drop it down here. And we can see, no matter what happens now, we have this new area, depends which line, I've gone for the black one there, ignoring the other two. I have this now, this greater number of particles that can react. So we have exactly met those expectations, that the catalyst increases the rate of the reaction by dropping the activation energy. Very, very important. So it decreases the activation energy by dropping the activation energy, and it does so. I realised I haven't actually mentioned this already, and I thought I had. So catalyst, well, I think it comes up in energetics again. So catalyst decreases the activation energy, and it does so by providing alternate an alternate pathway for the reaction to take place. If you're an A2 person, that will make a bit more sense. If you're not A2, don't worry about it. If you're doing A2, it'll make more sense. If you're not doing A2, just learn it and you'll be fine. So the key thing is it drops it down here. There are points where they have asked you to draw. I think in the past they have put lines on and they've said, oh, draw a line to show the activation energy with a catalyst, and you just need to draw it lower than this one. Basically, that's all they're looking for. So that's basically it in terms of looking at it in terms of temperature, and we've talked about catalyst. The other thing to think about is, and you can't really look at it in terms of energy here, but a separate point with the kinetics is, again, thinking about rates of reaction at GCSE. We can talk about concentration. Obviously, concentration, increase in a concentration is ultimately going to increase the rate of the reaction, and the reason is that in more molecules, we could say, or particles, I guess, more molecules in given volume, so therefore we're going to get more frequent collisions, of course, which is going to mean statistically more successful collisions. If you don't like the term statistically more, you could say there is a higher chance of successful collisions. So statistically more successful collisions, or a higher chance of successful collisions, and that's really the same point being made again. Something to be aware of, and I have seen this once asked, increase in concentration. They were quite sly one time, and they talked about it was actually an equilibrium, but the thing that was important was that they were talking about all of these were gases, and if we increase the pressure, the same thing happens. Increase the rate, because the same thing, we have more molecules in a given volume, more frequent collisions, and statistically or a higher chance of successful collisions. So increasing the pressure, if we're dealing with a gaseous situation, although you might be going, oh, equilibrium, I don't know what to do. The idea behind the equilibrium was it was talking about the rate of which the equilibrium is reached, and so it was still talking about kinetics. It was a kinetics question wholeheartedly. There was no actual equilibrium knowledge required. It was purely kinetics, but it just threw it into an equilibrium situation to make people, I guess, a bit confused. The reason that it worked was because they were gases. You increase the pressure, therefore the particles are closer together, more molecules in a given volume, more frequent collisions, and therefore statistically more successful collisions, or a high chance of successful collisions. And that's really it. That right there is kinetics in a nutshell. So I hope that's been of some help. Quite a nice topic to get in an exam. It's quite a nice, easy mark. Often comes at the start, question 1 or 2 normally. And I hope that's, as I say, I hope that's been of some help. Please do stick some comments on if you've got any problems. And there you go.